So we're going to be modeling today, which means we're going to be looking at actual situations, writing equations, and then using those equations to answer some questions. I asked you guys to read about logistic functions. Here are the key takeaways I hope that you had. The graph of a logistic function is kind of an S shape. It sort of starts out looking exponential, but then it kind of levels off. I need you to know that there are two horizontal asymptotes in a logistic function. There are always two horizontal asymptotes. And one of them is y equals 0. And the other one is y equals c. C stands for the carrying capacity. And then there's a couple of formats of the equations for logistic functions. You might have written those down in your notes. We're going to make sure we get them copied down today. Don't worry about trying to jot this down now. This will come back. But these two things you probably saw in there. And I got great news for you. These will be provided to you on the test. You do not have to memorize these. So you're going to have to deal with these things, but any problem where you have to use one of these formats, I will provide those to you on the test. Okay? My promise to you, if for some reason it's not on there, remind me and I'll write it up on the board. All right. We'll talk more about that when we get to it. Did you guys have any burning questions about logistics functions? All right, they're like more realistic exponential functions. Okay, well, here we go. Let's write some equations. So we're trying to model situations. Do you guys know how to deal with increases or decreases by a certain percentage? Like, are you aware, and this is probably going back to Algebra 1, but are you aware that you can take the amount that you have right now and you can just, if you're trying to increase or decrease by a percentage, you can just multiply it by one single number to make that happen? What would my special number be if I were increasing by 8%? It would be 1.08. And I could use a calculator and figure out what the new population is. More importantly, though, is do we understand where that 1.08 is coming from? So the $60 hoodie that's 30% off, so this time we're decreasing it by 30%. What's my special multiplier going to be this time? 0.7. All right, so the thought pattern is we always start with 100. We had a town, we started off with 100% of the population, and we added 8% on. That's where we got that 1.08. This 0.7 came from, again, we started at 100% of the cost of the hoodie, but we took 30% off, and that's where that 70% came from. We feeling okay about that? So that's one of the big things that we're going to see pop up in this section, is coming up with these multipliers. So a couple different ways to deal with exponential functions. The general exponential function model we talked about before, but when we're talking about a real world situation, this a value is going to be some initial value. Last class we talked about how that was, where we saw that on the graph. Do you guys remember where a was on our graph? The y-intercept. And then b is going to be your multiplier. And if it's a situation where we know there's a certain percent increase or decrease, like what we were finding here, those were our multipliers. In fact, both of these expressions kind of resemble exponential function. The only thing that they're missing is like an exponent on it. What would it mean if I put an x onto this thing? X would be how many times it's growing by 8%, right? So the whole idea of an exponent is that you're multiplying by something over and over and over again. So if I were just going to increase by 8% once, I'd multiply it by 1.08. But if I wanted to do that 5 times, because it's happening over 5 years or something, put an exponent of 5 on there. All right. This thing, not a huge fan of. but it's in the book. So I'll tell you, I'm never going to use this, but some of you might be equation collectors. So just for completion, P is the initial population. This is like a specialized version of this equation. My philosophy is, like, if I can have one tool that does 10 different things, I'd rather have one tool and know how to use it for 10 different things than to have a whole bunch of specialized tools for individual things. So, so this is one of those special things. If you're dealing with a population, look what they're doing. They're doing 1 plus, and then R is going to be your increase or decrease is a decimal. So for example, if you were doing an increase by 5%, then that would be 0.05. It's kind of like what we just did up here, right? You guys just mentally did the 1 plus the increase as a decimal here anyways. So in my mind, this seems like we should just use this. I don't know. But just in case, some people like collecting equations. There's something else we're going to do today, too. Do you guys remember half-life from last year? Yes? And did you enjoy that? It's pretty cool. It's super useful. It's one of those things that my students, a lot of times they come in and they're like, I hated half-life. I could never figure out which formulas to use. And we're not using formulas for half-life in this class. We're just going to use this thing. This thing will cover so many bases. All right, so let's use it. So we got these bacteria cells. They're bad bacteria cells, by the way. Not the good, healthy ones that live in our gut. These are bad ones. And we've got them in a lab, and we've got a colony growing. And there's 8,000 cells at the beginning, and then 22% of them are going to die off every hour. We might be spraying them with some new kind of antibacterial spray or something like that. So let's model what this thing's going to look like. So I'm going to write myself an equation. Let's just use y equals f of x if you prefer. Do we have a starting value? Yep. Some kind of multiplier. I'd say if 22% are dying every hour, then we want to be thinking about 100 minus 22, which is not 88. So my multiplier would be 0.78, and then to the x power. And when I'm doing these kind of application problems and writing an equation to model, I like to label what's what. This is the number of cells, and this is, what is x representing? Every hour. By the way, do you guys know what this symbol is called? The official lexicographic name for this symbol? The pound sign, the hashtag. It's called an octothorpe. Fancy. I don't know why. It has 9 spaces, but it's octo. I thought that was kind of weird. Octothorpe. That's octothorpe with an E on the end. It's like one of the old-fashioned fancy spellings. All right. Sorry for that side note. How many cells will there be at midnight? Ooh, you know what? When I said hours, I should have been more specific. X is the number of hours after noon, right? We said we're starting at noon, so that must be our starting point. So how many cells are there going to be at midnight? Are they giving us an x value or y value? X would be 12. Yeah. And obviously we could just plug some numbers into this thing. and punch it into our calculator, but we're going to do something fancier than that. We'll go ahead and write it down. But let's break these calculators out, because a lot of times the way we're going to be solving these equations, not this one, but the next one, is we're going to be solving them graphically for now. Until we develop the tools to be able to solve them algebraically, for right now we're going to be solving them graphically. So let's make ourselves a sketch off to the side here of what we expect our graph to look like before we type in the equation. This is going to be one of those sections where you've got to mess around with your window a bunch. Okay, and that can get kind of frustrating, because like you type in the equation, you hit graph, you don't see anything. Well, it's probably because your window's zoomed in way too far or way too far out. A good first step before you even type anything into your calculator is make a sketch of what it's going to look like and see if you can label some x and y values on that sketch. That'll help you figure out what your x min, x max, y min, y max should be. Okay, so what do we know about this thing? Is this exponential growth or decay? This is exponential decay. Well, we know what exponential decay looks like. It's going to be some graph that's curving down towards the x-axis like this, right? Do we know where it's going to start out right here? It's going to start at 8,000. We know that because that's our y-intercept. Do we know how long it's going to take to curve down? No, I really don't. So we're going to have to do some guesswork. I can tell you for certainty, if I go from 0 to, let's go a little bit above 8,000. What do you think, 10,000? If we go from 0 to 10,000 in the y direction, we should be pretty good. And then from 0 to, what do you want to guess? Give me a number for our right-hand edge of this. We definitely want it to be higher than 12. 24, yeah, 24 would be a good starting spot. We'd be looking at like one full day in the life of this colony. Well, death of this colony. Remember, they're bad bacteria cells. It's okay. We're happy that they're expiring. All right, so before I even type in my equation, I'm going to go to my window and get this set up. So in the x, we said we were going to go from 0 to 24. Do we want to have a tick mark every 1 hour, or do you want to space these out like every 3 hours or 6 hours? What do you think? 3 hours? I think that would be a good one. In the y direction, we said 0 to 10,000 would work pretty well. How often do we want to see a tick mark here? We certainly don't want a tick mark at every cell, because then we're going to have 10,000 tick marks up the side of this thing. What do you think? Every 1,000? Would that kind of make sense? Let's do every 1,000. Okay, now let's go into y equals and type this function in. 8,000 times 0.78 to the 12th. And oops, not to the 12th. I want my function. I need an x in there someplace. Did anybody else make that same mistake when you're typing it in? No, you guys put your x in. Good for you. That's awesome. Doing better than me this morning. All right, let's see what we see. Hey, that's exactly what, look at that. That's like I could have traced it. That's pretty good. All right, so we could go back to the home screen and type this in, but there's a quicker way. Now that this function's in our calculator, do you guys remember the quick way to tell your calculator an x value and have it evaluate? That second calc value. So go to your calculate menu, choose that first option. It's going to ask you what x value you're interested. I'm interested in an x value of 12. Looks like about 405 cells. Cool. All right. Questions so far? All right, so this next one's asking us when are half of the cells going to be dead? And I need you to understand that that is the half-life. That's what half-life means. Half-life is how long it takes before half of something goes away. So we use it in like medicine a lot. Drugs stay in your system. There's usually a half-life for that. We use it for radioactive decay. So we need to solve an equation. So here was my model. This time they're giving me a value not for x but for y. What is the special y value that they're hinting at when they say half-life or half of them are dead? 4,000. So we need to now solve this equation, but we're putting 4,000 in for y this time and solving for x. Some of you may remember how to solve when x is in an exponent. We're going to deal with that later on in the unit. But for right now, anytime we're solving for x that's in an exponent, we're just going to use the calculator to do this for us. So the way we will handle this is we're going to graph a second function in our calculator. It's going to be a flat line at 4,000. We're going to graph this, and then what are we going to do? We're going to look at where they cross each other. Because wherever they cross each other should be 4,000, something comma 4,000, and that something is going to answer our question here. So go back to your y equals, go down to y2, and we're just putting in 4,000, y equals 4,000. And when you hit graph again, this time you're going to have a horizontal line that goes across. And we just need to know the coordinates of that intersection there. Have we talked about how to find intersections yet? No? Where do you think you might find it? In second calc, yeah, that's where all the useful stuff is. Which of those options do you think might help us find where two things intersect each other? Option 5, is it? Yep. Are you sure you haven't seen this? Now, these are going to ask you some different questions. So it's going to ask you for first curve, second curve. The up and down arrow will change between your different equations up here. So when they're asking you for first curve, second curve, they're basically asking you which two of these functions do you want to find the intersection for. Usually, you can just hit enter twice, because usually you're only going to have two equations in there. But if for some reason you were comparing like 5 different functions and you wanted to make sure that I want to find the intersection between y2 and y5, this is where you're going to tell the calculator to focus on these two special functions. Does that make sense? So since I only have 2, I'm just going to hit enter once and twice. And then guess, we're kind of familiar with this. You have control over your cursor, moving it left and right. Move it so that it's kind of close to that intersection, and it'll do its thing and spit out a value for us, which comes out to be about, if I'm doing 2 decimal places, that would be 2.79. .79. So there are kind of 2 questions being asked here. One of them was, what is the half-life? Let's go ahead and write what the half-life is. How long did it take for half of them to die? 2.79 years, hours. I have a very heavy conceptual question for you. You guys ready for this? Imagine we're right here in time. There's 4,000 cells left. Okay? If I sat there and watched this petri dish until there were only 2,000 cells left, how much longer am I going to have to sit here? There's 4,000 right now. How much longer is it going to take before there's only 2,000? Answer is 2.79 hours. In 2.79 hours, I'm going to have 2,000 cells. How many hours after that am I going to have 1,000 cells? 2.79 hours. How many hours after that am I going to have 500 cells? 2.79 hours. And after that, how many am I going to have? 250 cells. 2.79 hours. Every 2.79 hours, you're losing half of whatever you started with. Does that? That's the concept of half-life, right? Okay. So the half-life is 2.79 hours. They did ask when is this going to happen, and since they gave us the time that it started, we should probably be specific. It's going to happen in the afternoon sometime, right? 2 hours plus a little bit more. I challenge you to find me the time to the nearest minute. Can you find me the time to the nearest minute? I'm reaching for my calculator here. Spoiler alert, it's not 279. And that's in the afternoon, so that'd be PM. Is that what y'all came up with? Here's how I did it. Is that what you guys did? That's 2 hours plus another 0.79 of an hour. And if we're talking minutes, 0.79 of, there's 60 minutes in an hour. So 79% of 60 minutes would be 47.4 minutes. So about 2:47 is when that would happen. All right. How are we doing, guys? So far, so good? All right. So let's see what we can do with this. Well, this is going to be interesting. Baseball cards. So we've got this. It must be a pretty special card. It was worth $870 5 years ago. And today it sold for $1,225. Wow. So we want to know what the annual appreciation rate. Appreciation means what percent is it going up or down? This might be a good one to set up a little table or something because there's a lot of numbers going on here. And I think it would help me anyways to be organized to set up a table. So I'm going to do that. So X and Y. We need to choose what's going to be X and what's going to be Y. Y is the thing that the problem is about. And I would say that this problem is about the value, right? It's about money. So I'm gonna have my Y be the money, and then X would be the year. So at some point it was worth $870, and then at some point in the future it was worth $1,225. And then we just need some numbers for X, and this is, remember, one of the cool things about exponential functions is it's totally arbitrary. You can have these numbers be anything you want. This one, whatever this one is, it should be 5 more than whatever this one is. What special X value would be helpful for us to write our equation, though? If we could get a 0 in one of these spots, then we would know what A is, right? So my question for you is, do you want the 870 to be 0, or do you want the 1225 to be 0? 1225 is right now, so there's something to be said for having this be 0. And this is 5 years ago, so we would make this what? If this was 0, then we could make this -5. And that does kind of correspond to 5 years ago. Do you guys want to do it that way, or do you want to say, okay, we started at 5 years ago, that was year 0, and now we're on year 5? You don't want to deal with the negatives? All right. I'm going to deal with the negatives. I'm going with this. I'm going to say this. Today is the start. Today is the start of the rest of your life. 5 years ago, it was that. I'm starting it today. I'm sorry. Some of you don't agree with me. You're welcome to do it the other way. You'll get the same answer. Promise you. You will. All right. What's my annual appreciation rate? So I think what we want to do here is, well, let's start writing an equation. We know our A value, right? 12 1225. That B value would be my multiplier. If I knew that, I could tell you what the increase or decrease was, but I don't know it. So what are we going to do? We're going to leave it as a variable, and we're going to solve for it. In order to solve for it, we will need to find some x and y values that we can substitute in. So this is, you guys did some problems like this in your assignment, right? They weren't word problems. You got a graph with points, but we've got a table with points. We'll do it the same way. So 870 equals 1225 times b to the negative 5. And we'll do a little bit of algebra to figure out what this is. So let's divide on both sides by 1225. And then how do we get rid of that negative 5 exponent on the b? It's going to be kind of weird. We got to take a negative 5th root. What does that even mean? I'm pretty sure our calculator can handle this. So you're going to type in the negative 5 first, and then it's under the math button that you will find your general root, the one with the little x on it. That's going to take a negative 5th root of, I'm going to make a little mistake here, because it's a common one that I've seen. That is not the value that I'm looking for. What did I forget to do when I typed in? I need those parentheses around my fraction, right? Calculator's not smart enough to know that I wanted to do the top and bottom of my fraction to a negative 5th root. So let me fix that. Now some of you have the fancy thing where it just puts the square root bar there, so that's automatically going to group stuff together, but mine's not that fancy. Something weird's going on here. It's negative 5 with the x root. I think I need to actually put a parenthesis around the negative 5 as well. Maybe it was not so smart to use the 0 and negative 5. Maybe we should have gone with the 0 and the 5. It's all right, we got this. Well, so first of all, does this seem right? I looked at this and like, that doesn't seem right. First of all, it's a negative number. B can't be a negative number for an exponential. Yeah. And then the other thing I was looking at, when I first saw this, I was like, 0.93, that means we're losing 7% of the value each year. That doesn't make sense. Isn't this baseball card getting worth more over time? So I know something's not right there. And I think that's it. I think my calculator is not smart enough. The same way when you square a negative, I don't think it's smart enough to know that I want to do the negative root unless I explicitly tell it. So, all right, so lesson learned. Negative roots need a parenthesis around the value of the root, and if you've got a fraction in there, we want a parenthesis there as well. So 1225, please work. 1.708. That seems more reasonable. That would be an increase over time, right? Because it's bigger than 1. So I'm going to go ahead and write that down. So B is about 1.0708. And since it looks like we're going to have some follow-up questions here, I'm going to go ahead and stow that so we can easily use that nice long decimal answer later without having to type it in again. So I'm stowing it into B. We can answer one of our questions right now, I believe. What is the appreciation rate? What percent are we increasing by each year? About 7.08%. So my appreciation is about 7.08%. That's a pretty good investment year on year. Once you get out in the adult world and you start looking at retirement investments, you'd be happy to get a nice 7% return on investment. All right, to answer the rest of these questions, let's use the calculator, because it looks like we're doing a how long and a how much is it going to be worth 20 years from now. So we're going to need an equation. Let's go ahead and write our full equation now. Y equals 1225 times 1.0708 to the x power. We'll type that into our calculator, and then we're going to need to probably reset our window. So let's think about what this one's going to look like. Is this growth or decay? It's definitely growth because the price is going up. And I know that exponential growth has a curve that's going upwards like this. Do we know where it intersects the y-axis? That should be 1225, yep. And do we know how high we want this thing to go? I'm reading ahead. They want us to look at a value of 500,000. So I think we better go a little bit higher than 500,000. So I'm going to have my graph go up to 600,000. And then this is something that I've just learned over time. A lot of times you're going to want it to go down below 0 also, because the x and y information kind of drowns out what's going on at the bottom of the graph. It sort of covers it up. So I'm going to make mine go down to maybe negative 100,000. And then let's talk about in terms of time. When I graph this thing, I think I want to see. I think I want to see a little bit of the past. I would feel a lot better about things if I could double check and make sure that this card was valued at 875 years ago. So in terms of my x's, I'm going to have it go back in time. Maybe let's have it go back in time 10 years. And how far forward in time? Your guess is as good as mine. I don't know. You want 50 years? 100 years? Let's try 50. All right, so I'm going to go ahead and set this thing up. So I'll warn you that finding a good window will be like one of the more challenging things for you probably on this assignment. You just got to kind of sit and think about, and you're going to get it wrong. You have to go back and adjust it and try something else until it works, and it'll be okay. But the best advice I can give you is make a sketch of the graph first and then try and think through it before you start typing stuff in. So my x is going from negative 10 to 50. I know that'll get me back far enough in time. I don't know if 50 is going to be enough time, but we'll leave it like that. I'm going to put tick marks every, 5 years. I want my y to go from negative 100,000 to 600,000. Then I'll type in my equation. Hey, and remember when you type in your equation, you don't need to type out 1.0708, right? Because why? We stowed it. It's in B. It's already there. While we're doing this, should we go ahead and graph a horizontal line someplace? What's the y value we're going to eventually be interested in our follow-up question? We're eventually going to want a horizontal line here. Let's not worry about that for right now, though. Let's just graph this thing. I hope that we can kind of see what's going on. Oh, boy, this is not looking promising. Woo! Okay, so little trial and error here. What went wrong? Can you see an exponential curve? I can. Do you see this little thing over here? It's trying its best. What do I need to adjust? I don't think we went far enough here. It is increasing. It's just we need to increase way up to here, and it hasn't even gotten close. In 50 years, it's not even close. So let's go back to our window. We said we weren't sure on the x. So let's go back here. 100 maybe. Could be. We might need more than that, but let's try it. All right, that's looking more exponential-ish. Oh, yeah. Hey, there we go. I didn't think that was going to make it, but I think 100 gets us there. I want to do a couple quick things and make sure I'm feeling pretty good about my model. I'm going to plug in these x values and make sure that we're getting these y values. If I get exactly 870 and 1225 or something very, very close to it, then I'm going to be feeling pretty good. I just want to check and make sure I didn't make a mistake typing something in or in my math. So I'm going to go second calc value. I'll tell the calculator I'm interested in x value of -5. Fingers crossed that we get 870 on the money. And then if I do the same thing for 0, I'm hoping I get 1225. And we do. Okay. So the 2 points that they gave us are on our graph. That's making me feel pretty good about this. So what else do they want to know? So they want to know 20 years from now, how much is it going to be worth? So 20 years from now, it's going to be worth, well, our calculator will do that for us. We were just given it x values. Let's just give it an x value of 20. A whopping $4,815. And then they wanted to know how long it was going to take before it was worth $500,000. I think it's going to be a disappointing answer, guys. We're going to be waiting a long time. So this time we know a y value of 500,000. How are we going to find that? Same way we did before. We'll go ahead and graph a horizontal line at 500,000 and see where that line intersects her. I think so. I need to go back to y equals and put in a line at 500,000. Sorry, 88 years. I mean, it's a lot of money, but that's a long time to wait. Yeah, okay, there you go. That's good. That's good thinking. Generational thinking. Maybe your grandchildren will enjoy that $500,000. Of course, in 87 years, $500,000 isn't going to be like $500,000 is now. You're not going to be buying a house for $500,000 in 88 years, probably. Maybe a car. It's inflation. We're going to talk more about that kind of stuff later on. It's going to be awesome. But yeah, it's about 80. We'll just say 88 years. All right. Questions on that one? Yes. Yeah, that's a great question. So anytime we're doing application stuff on a test, my goal is to be very clear on what I want you to round to. But we make mistakes too. So if that information is ever not available to you and it's a testing situation, you're welcome to ask. Yeah. On your assignments, do what you think feels right. They might give you instructions, they may not. You're going to be checking your answers in the back of the book. That should give you an idea of what they thought, but that doesn't mean just that because they have PhDs in math doesn't mean they're smarter than you about that kind of thing. So, yeah, great question. Thank you. Any other questions about that one before we move on? Folks, I think we're going to skip this one at the bottom for the sake of time because you did a couple of problems just like this in your assignment, and I didn't have any questions about those. So let's move on. Half-life or logistic. They never gave us a schedule. I have no idea what time this assembly starts. So let's do the logistic one first. Let's get this one out of the way. Not that it's like bad or anything. Could you guys write those two formats down? Those are in your textbook. Remember I said on an assessment I will provide those for you. And if for some reason I forget, please remind me and I will put them on the board. They're both valid ways of doing these problems. Most of my students will tend towards the first one. I'm not sure why. Maybe it's because of the negative value in this exponent here. Also, sometimes people are a little bit afraid of e. I'm not sure why. E is a really cool number. Like in terms of like cool numbers, there's pi and there's e, and I would kind of say that e is cooler than pi. It's a close call, but e is pretty amazing. Next year in calculus, you're gonna learn like the coolest thing about e. But it's super useful. The entire financial world runs on that number. And like pi, it's one of those long decimals that goes on forever and ever. Anyways, I'm gonna stick with this because this seems to be the preference of most of my students. Okay, so let's try and understand the situation. We've got a lake. There's 200 trout to begin with. 2 years later, we've got some more trout. Is the population going to keep increasing forever and ever and ever? No, at a certain point, there's not going to be enough water in the lake, enough nutrients for everything to survive. So there's some ecologist comes around, does some measurements, and they say, yeah, 850 is about as many trout as we're ever going to see in this pond. So we want to make a model and answer some questions about it. So I like to start this by sketching a graph. And thinking about what my window settings are going to be, since we're going to need to graph this in a minute. I'm going to have my x-axis be just a little bit off of the bottom. Again, I like to leave a little bit of space under the x-axis when I'm graphing, because that's where like the numbers end up when you're doing your analysis piece, and I don't want those covering up my graph. That's just my thing. So I'm going to have this be 0 here, and because it's a logistic function, we know that that is a horizontal asymptote. We know that a logistic function is going to curve upwards, but then eventually level out. Something like that. And we know that there will be another horizontal asymptote at that level out spot. And can you give me a value for that other asymptote? 850. So the pond's never going to have more than 850. We're going to get closer and closer and closer. Technically, the logistic function will never hit 850, but it'll get close enough that we'll round to it, right? What else do I know? I think they gave us some coordinates for some point on this thing, didn't they? 2 years later, so 2 years in, we're going to be at 315. Oh, I didn't do the 200 yet. The 200 would be my y-intercept, right? If we're starting right here, 200 would be how many fish there were when we started. And then 2 years later, there's 315. So I have no idea where on the screen this is going to end up, but I know that 2, 315 should be on my graph someplace. We got a lot of moving parts going on here. Okay, are you guys ready? We're going to do some pretty intense algebra right now. We got this, though. We got this. All right, we're going to stick with this model here. And I want to go ahead and write it down and start filling in some values. So what I know is that C is the carrying capacity, always. C is the carrying capacity. So I know I'm going to have an 850 on the top of this thing because C is always going to be the carrying capacity. And then I want you to write one other note about this equation. A in this equation is not the y-intercept. A is not the y-intercept in this thing. Okay, so it's kind of related to the exponential function, but that A is not the y-intercept. So right now I am missing 2 values. I'm missing an A and a B. Now we've talked about how to find one value in an equation. If we're missing one thing in an equation, what's the big idea there? We did it last time. How do we solve for the missing piece if we're missing one thing in our equation? We plug in an x and a y value. We pick some point that we know is on the graph and we plug that in, right? We're missing two parameters here, two values. We're going to need 2 points. And we're going to have to plug it in twice, okay? So we know that this point's on here. We will end up using this. What is the other point that we know both an x and a y coordinate for at this point? 0, 200. We know the coordinates of this point here too. When you do this, you always want to start with, for these problems, you always want to start with the 0, whatever. Start with that y-intercept. So we're going to use 0, 200 and pop those values in for x and y. And as you can finish writing that equation down, you're going to see why we chose to do the y-intercept first. Are you seeing it? When we do the y-intercept, we're going to have a 0. And why is 0 making this easy? This whole thing just turns into a 1, right? This b to the 0 is equal to 1. So this equation is really just 200 equals 850 over 1 plus a. You guys know how to solve that. I'm going to write this. I don't usually write this down as a separate step, but we got notes, right? So, all right. We solved much more complicated equations than that in our last chapter. Go ahead and solve that. If you need a reminder, we're going to start by busting our fractions. This one actually, if you divide this, it's going to come out to a nice, clean, terminating decimal. A lot of times when you're doing these, that won't happen. In that case, you want to keep it as a reduced fraction. So I asked my calculator to do 650 over 200 and turn it into a fraction. You guys remember where the frac thing is in your calculator? 650, yeah. Because I multiplied the 200 times the 1 and the a. That gave me a 200. When I subtracted that on both sides, I got 650. I think. Did I make any mistakes here? Are we good? Okay. All right, so my calculator says that that's 13 over 4. So great. That is so cool. So now we can, I'm going to go back to here and rewrite this. I've got y equals 850 over 1 plus 13 over 4 times b to the x. Cool. Now I only have one parameter left. How are we going to find it? Put that other point in there. So now we can take our other point, 2, 315, and stick that into here. Now this is a pretty involved process. I told you guys we're going to do some pretty intense algebra here. But you got it. 315 is y. Oops. B's not 315. X is 315. That's a great question. That was supposed to be a 2, wasn't it? Jeez. I made one mistake and then I corrected it with another one. Thank you for helping me out there. All right, can we solve this? Absolutely. Clear your fractions. Start by clearing your fractions. You're going to multiply by your denominator on both sides, which is 1 plus 13 over 4b to the second. At this point, folks, I'm hopeful that you're actually doing the problem and not just copying down my steps. Let's see, 315 times 13 over 4. We'll math frac that too. Every year somebody figures out that it's actually easier not to distribute this thing over here. Is anybody leaving it there and just dividing it on both sides? Yeah. I just can't resist distributing. Like, I'm like, oh, there's a number here. I'm multiplying it by two things. You don't have to distribute this 315. Once you do that, it's equal to 850. You could just divide 850 by 315, then you just have the 1 plus whatever over there. But anyways, I distributed. I'm feeling okay about it. I don't know what 850 minus 315 is. 535, thank you. 535, got this big old messy fractions to deal with. Grumble, grumble. And then I think we just take a square root and we're good, right? I'm just gonna leave it all like that. Let the calculator do all the simplifying. And then I'm definitely stowing this one in B so that I don't have to type all this stuff out again. So square root of 535 times 4 divided by 4095. Stow B. Did I make a mistake here? Something seems. Yeah, so I multiplied by the reciprocal over here. So, but you're right. Division is the same as multiplying by a reciprocal. Yeah, good question. Thank you. So B ends up being about 0.7229, but of course we're going to stow that so that we can use all of its decimals. Questions here? So the algebra gets a little intense here. Just take it a little piece at a time. If it helps you to show your minus 315 on both sides, go ahead and do that. All right, let's graph this thing. Once again, I don't really know how far out my x is going to go. I know 2, it's there. I'm just going to guess 20 years. I don't know. We'll see. We kind of biffed it last time, but we were able to recover. I want it to go above 850, so I'm going to have it go up to 900 and maybe have it go down to negative 100. So, and then I'll go 0 to 20 in the x. And if you get in the habit of writing these things down on your little sketch, that's going to help you come up with better windows more quickly. The one thing I'm not sure if is 20 is going to be too much or too little. Last time we tried 20 and it was way too little. We had to go up to 100. All right, we don't have anything to graph yet. I need to type my equation in. And it's this, except with my b value stowed away in it. So I'm just going to use the b on there. Keep in mind, since you have a fraction, you must put parentheses around the entire denominator. And we'll hit the graph button and hope that we see something like what we were expecting. Did it work? Ish. Hey, look, yeah, it's going up. Is it going to level off? Nice. It worked out pretty well. I'm going to check that these 2 points are on here. That'll make me feel even better about this. So if I ask my calculator if I tell it I want an x value of 0, it's giving me back 200. That makes me feel great. This one is really going to be my confidence booster. I give it 2. It tells me, oh, 315. Nice. All right, so we've matched all the pieces. Now it's time to answer the question. They want to know, when are we going to get 700 trout in this thing? So that's a y value, right? So we're going to need a horizontal line at 700 so we can find that intersection. I have found with logistic functions and with exponential functions with the intersect, you can just hit enter 3 times. If it's your only 3, like your guess doesn't need to be anywhere close to it and it will still find it. The main reason for that guess is if you have multiple intersections, like your calculator will know which one to find, so the guess helps you find it in that case. But there's only one usually. So looks like about 8 years from now. Now, if this is a real world problem, why would they want to know that? Maybe in this little mountain lake, they decide they're going to open up fishing once you get enough trout in there, right? So then 700's the magic number for this thing. So in that situation, what would a good answer be? 8.37 years from now? Like if the fishing society called and was like, hey, how long till we can fish in this lake? Well, 8.37 years from now. Is that what you'd say? You would say 8? Ooh, are there going to be 700 trout in there after 8 years, though? I'd probably say 9 years. 9 years will be safe. We should be above it at 9 years. In the real world, they would probably put a little bit of like smudge factor in at the end of that and just say, yeah, 10. Just to be safe, we'll go 10. All right. There is going to be one of these problems on the test. This is going to look daunting to you right now, probably. And then when you do your first one, it's going to feel a little daunting, but once you do a couple of them, it'll be okay. Let me get this here. Uh-oh. That I actually looked this up, that the half-life is 5 hours. Now let's make sure we understand what this means. If I drink a coffee that has 300 milligrams of caffeine in it, that much caffeine goes into my bloodstream pretty quickly. Not immediately, but pretty quickly. How much caffeine is going to be in my bloodstream 5 hours from now? Half of that, which would be, what, 155 or something like that? And then another hour after that, it's going to be how much? Whatever half of that 155, 70-ish, 77-ish, something like that. And then another 5 hours after that, there's still going to be half of that left over, right? Which is kind of interesting when you think about, like, people say don't drink caffeine in the afternoon or before bed. Like, it does stay in your system for quite a while. 5 hours later, you've still got half of that caffeine still rolling around in you. That's assuming you haven't had another one, right? So And this is how most drugs work. Things that go into your bloodstream, your liver is going to remove them from your bloodstream slowly over time, but there's going to be some of it left in your system, like indefinitely. Now, like 100 years, if you live to be 100 years old, are you still going to have a little bit of that caffeine knocking around in your system? Probably not, but like theoretically, it never really goes away. There's always a little bit in there. On the span of probably a week, most of that, 99.9 is gone away. Okay, let's write a model for this. This is not logistic because we're not running up against something that's limiting us. And I might actually start with a graph of this. Does this seem like growth or decay to you? Decay because we're losing caffeine out of our bloodstream. So we're going to be going down like that. We know how much we started with. 310. And then we do have a point on this graph. I'm going to stick it right about here, and I'm going to label it 5, comma, what? 5, comma, 155. Because after 5 hours, half of it's gone. I could put a bunch more points on here, 10, comma, whatever half of that is, 177-ish. But I think that 1 point's probably going to be enough for us to write our model. So let's do it. Y equals, we know what our A value is. Since this is exponential, it's 310. Don't know B yet, but we know how to find it. And this time around, since we're only missing one value, one parameter, we only need to plug in 1 point. We do not want to use the 0, 310 because we already used it here. So let's use that 5 and 155. When you do these half-life problems, you're going to find, well, something kind of interesting. This step right here is always going to end up coming up for a half-life problem. It's always going to look, no matter what your starting value is, you're always going to end up here. If it's a half-life problem, you're always going to end up at 1/2 equals b to the x. Because why? Because if we're talking half-life, oh, that should say the 5th, shouldn't it? I'm sorry, I left out my 5. You guys are giving me like confusing looks. Like I must have done something wrong. Okay, here we go. You're always going to end up with 1/2 equals b to some power. Because why? Because if it's half-life, this is always going to be half of this. Make a mental note or maybe even a physical one in here. You're going to run into a problem in your homework where they don't tell you what the starting value is. I'll tell you, it doesn't matter. Make it up. Make it up whatever you want. This problem would be no different if I started with 100 and ended up at 50. Or if I'd put 2 here and 1 here. Half-life formulas that you might have learned last year exist because you're always basically dealing with a half somewhere. So on the one that you run into in your assignment, if they don't give you a starting value, just make one up. Anything you want, any number you want, and then cut it in half for that later point. Okay, so the 5th root of 0.5. B ends up being about 0.87, we'll go 3 decimals, 871. But of course we'll go ahead and stow it so we keep all of our decimal points in there. Now, does that number seem reasonable to you? Does that match what a B value should be for something that's decaying, something that's decreasing? How much percent is your body removing from your bloodstream every hour. It's keeping 87. How much is it removing? About 13%. All right, cool. Now we should be able to answer all these questions because we got a nice model. Go ahead and write it down since I got a little space here. So y equals 310 times about 0.871 to the x power. And we can graph it and then use our calculator to answer the rest of it. Let's think about our window first. I need to go up to 310 to see the beginning of it, so I think I'll have my graph go up to 400 and maybe down to negative 100. I always like to go a little bit below 0 on the y. For the x, we can start at 0. That would be this, when we drink the coffee. How far out am I going to want to go? 10, 12? You want to go 24 again, since that would be like a full day? Yeah, sure. That sounds good. And then we'll get that set up. So I'm going negative, did I write negative 1,000? No, that's a negative 100 and then a 0. But I'm flipping my x's and y's. I don't know. That should work. Yeah, has anybody made that mistake today? Like you get your Windows set up and you hit graph and you're like, why can't I see any? Oh, wait, I didn't type in the equation yet. I do that all the time. Should we go ahead and graph a horizontal line while we're here? A lot of times they ask us about something. 12 hours, that would be an x value. Oh, here we go, 155, right? Actually, we don't need this to do 155. We already figured out how long it took to get to 155, right? Because that's half of the original. That one's done. Last one says how long till 95% of the caffeine is removed. So we're going to need to figure out what, if 95 is removed, that means we got 5% left, right? What's 5% of 310? 5% of 310 would be 0.05 times 310, right? Actually, I don't even need to know what it is. I can, because I'm just going to graph it anyways, right? 0.05 times 310. It is 15.5, right? But you can just type it in your calc. It'll do a horizontal line at the right place now. Okay, fingers crossed. Are we seeing what we want? Yeah, it's pretty good. Are we going to get an intersection? Ooh, it's hard to tell if the intersection happened there or not. It did? Second calc intersects. If it gives you an error when you try and intersect, that might be because your intersection's off the screen. Ours is just on the screen. $21.6 hours is how much to remove 95% of it. And I did not answer the middle question there yet. That would be an x value, right? X equals 12. We know how to put in an x value. Wow, almost 60 milligrams still in your body after 12 hours. It's like a cup of tea. All right. So a couple of big ideas for today. One of them is, you guys feel comfortable that you can set up a window and maybe play around with the window a little bit to get what you want to see? That's going to be one of the more challenging things. And then using that technique that we've been practicing where we plug in an X and a Y value to come up with our missing pieces. When you get to the logistic problem in your assignment, would you guys please just have these notes out in front of you and just kind of follow along the same steps that we did here, and just be persistent. Things get messy, but we're going to start dealing with some messier algebra in here.